Okay, hi. I am working through the linear independence problems so that you have a pretty good idea of how I would do them, and we will kind of get there from here. I hope you all are healthy and safe and all of that good stuff. So let's take a look at problem number one, which has like three parts here. We're working with this set S that has three vectors in it. Um, so S is a set of three vectors, 2, 0, 7, 2, 4, 5, and 2, negative 12, 13. Okay. We want to write the vector. So our goal here is to write the vector negative 1, positive 5, negative 6 is a linear combination of these three. So literally that means you want to take some coefficient times 207 and add that to another coefficient times 245 and add that to a third coefficient times 2, negative 12, 13, and then you want that to be equal to negative 1, 5, negative 6. So this could be viewed as a system of equations where we take 2 times C1 plus 2 times C2 plus 2 times C3, and we get negative 1. So that's coming from the first element of each vector, the first component of each vector. And then we have 0 times C1 plus 4 times C2 minus 12 times C3. And we want that to be equal to 5. And then we have 7 times C1 plus 5 times C2 plus 13 times C3, and we're going to have that equal to 7. Or, sorry, not 7. Whoops, careful. That one's negative 6, right? Okay, so this is solving a system of equations. We know how to do that. We go 2, 2, 2, negative 1, 0, 4, negative 12, 5, 7, 5, 13, negative 6. You can use MATLAB to Gauss-Jordan that. I have the result here. Gives me 104, negative 7 fourths, 0, 1, negative 3, 5 fourths, 0, 0, 0, 0, right? So if I kind of think about this, this tells me that C1 plus 4C3 is negative 7 fourths, and C2 minus 3C3 is equal to 5 fourths, right? So I'm going to parameterize that, and if I let C3 be T, then C1 would be negative 7 fourths minus 4T, and C2 would then be 5 fourths plus 3T. So the easiest way to get a particular solution here is just let T be 0, right? So that means C1 would be negative 7 fourths, C2 would be 5 fourths, C3 would be 0. And if you do that linear combination, you let C1 here be the negative 7 fourths, C2 here be the 5 fourths, and C3 here be the 0, you should be able to work out that that gets you negative 1, 5, negative 6. So that's part A, right? So let's take a look at part B, which is a very similar problem as a slightly different outcome. Okay, so in part B, we're trying to show that we can make a linear combination of these and get a third, and a half. So just by the similar logic, I can build the same matrix. 2, 2, 2, 0, 4, negative 12, 7, 5, 13. But now I want a third, and a half, right? So if we apply Gauss-Jordan to that, we end up with 1, 0, 0, negative 1/6, 0, 1, 0, 1/3, 0, 0, 1, 0, right? So what do I have here? This means I have a unique solution, right? So my unique solution here is going to be that if I take negative 1/6 times the 207 plus a third times 245 plus 0 times 3, negative 12, 13, I'm going to get a third, a half. And that's the only way that you can combine these three things and come up with a third, and a half. So that's part B of problem 1 there. So let's look at part C. So part C is a similar problem again, but now we want to come up with 2, 20, negative 3. So again, I build that same matrix, 2, 2, 2, 0, 4, negative 12, 7, 5, 13. And now I throw in there 2, 20, negative 3. We apply Gauss-Jordan. We end up with 1, 0, 4, negative 4, 0, 1, negative 3, 5, 0, 0, 0, 0. Okay, so this is like very similar to before. The first equation reads as C1 plus 4C3 is equal to negative 4. C2 minus 3C3 is equal to 5. So what do? We let C3 be t. This is going to imply that C1 is negative 4 minus 4t, right? C2 will be 5 plus 3t, right? So to get a specific solution, just let t be 0 again. That means that C1 is negative 4. C2 is 5 and C3 is 0. This would make a specific solution. So what we're saying here is that negative 4 times 207 plus 5 times 245 plus 0 times 2, negative 12, 13 should give me 220, negative 3. Now that's not a unique solution. It is a solution that works for me. All right, so there you go. Okay, so let's take a look at problem number 2 here. 2 is about spanning, right? So we have this set S that has 3 vectors, 4, 7, 3. Negative 1, 2, 6, and 2, negative 3, 5. And we want to say that this spans, so if I take the span of S, we want to say that that's R3. All right, so what does this mean? This means that every element in R3 can be made as a linear combination of the 3 vectors of S. So the idea here is that so for every, let's call it A1, A2, A3, which is an element of R3, there exists C1, C2, C3, right, which are elements of the reals where C1 times 473 plus C2 times negative 1, 2, 6 plus C3 times 2, negative 3, 5 equals A1, A2, A3. So I can make a linear combination of the three vectors in S, can get any. The right linear combination will give me every single element in R3. All right, so there's a system of equations to this, right? So 4C1 minus C2 plus 2C3 would equal A1, right? 7C1 plus 2C2 minus 3C3 would equal A2. 3C1 plus 6C2 plus 5C3 is going to equal A3, right? So instead of building this into an augmented matrix, I'm going to build it into a matrix equation. 4, negative 1, 2, 7, 2, negative 3, 3, 6, 5 times C1, C2, C3 is going to equal A1, A2, A3. Okay, so let's call this one P, let's call this one C, have that equal A, right? So if this is the case, if there's a solution to this system, then like I have PC is equal to A, then this should imply that C is equal to P inverse A. I just took the inverse of P on both sides. If there's a solution, P inverse has to exist. If P inverse exists, this means that the determinant of P cannot be 0. So it suffices to show that if the determinant of P is not 0, then P inverse exists. If P inverses exist, this has a unique solution. So regardless of what A1, A2, and A3 is, I can find C1, C2, C3 in such a way that I can make the linear combination and get everything in R3. Stop and think about how that works. So all I need to do here is take the determinant of 4, negative 1, 2, 7, 2, negative 3, 3, 6, 5, which if you work this out or do it with MATLAB, happens to be 66, which is nowhere near 0, which means that S spans R3. And there you have it. All right, so that's problem number 2. All right, so problem number 3 is pretty straight up. We want to show that something is linearly dependent, right? So here's how this works out. Like, let C1 times the first vector, right, plus C2 times the second vector plus C3 times the third vector equal the 0 vector, right? If I let that happen, and I can get something other than C1, C2, C3 being 0, 0, 0, then I am linearly dependent, because if it is linearly independent, all three of those coefficients have to be 0. All right, so build your system of equations again, right? If I build the system of equations and I try to solve this thing, I'm going to get negative 2, 2, 2, 0, 1, 9, 3, 0, 3, negative 3, negative 3, 0, right? So that's what I've got. All right, so if I do that and I run RREF, I end up with 1, 0, negative 3/5, 0, 0, 1, 2/5, 0, 0, 0, 0, 0. All right, so what do I do? this gives me that C1 minus 3/5 C3 is 0, C2 plus 2/5 times C3 is 0. So just let C3 be something like 5. If C3 is 5, C1 minus 3 is 0, so C1 has to be 3. C2 plus 2 is 0, so C2 has to be negative 2, which means that if I take 3 times negative 2, 1, 3, plus minus 2 times 2, 9, negative 3, plus 5 times 2, 3, negative 3, I get 0, 0, 0, which means that I can have a linear combination that's not the trivial case of 0 plus 0 plus 0 and get the 0 vector, which means I am linearly dependent. All right, so there you go. That is number 3. How about that? All right, so number 4 follows the same exact logic as number 3. All we want to show is that if you put these things in, you're going to get the trivial case. So we just put the 4 vectors in as columns: 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1. We set that equal to the 0 vector. I do Gauss-Jordan. And lo and behold, I get 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, which is telling me that C1 has to be equal to C2, which has to equal C3, which has to equal C4, which has to equal 0, which means that I am linearly independent. Because if this set of vectors, if you take a linear combination of this set of vectors and you get the 0 vector, then all the coefficients of the linear combination must be 0. Okay, there you go. All right, so let's look at number 5. It gives me these 3 vectors, right? T1, 1. It gives me 1T1, and it gives me 1, 1T. Now, it's really, really clear that if I let T equal 1, that I'm going to get 1, 1, 1, 1, 1, 1, 1, 1, 1, which under no circumstances is this thing linearly independent. Because like you can just like take the first one and multiply by 1, the second one by -1, and leave the third one 0, and you're going to get the 0 vector, right? So that's like if I take 0 or 1 times this, -1 times this, and 0 times this, I'm going to get the 0 vector, which is non-trivial, which means it's a linearly dependent. Okay, so that's the one value it can't be. Now, if I build this matrix, right, and I let T be anything other than 1, what you can do is you can Sims T in MATLAB. And if you Sims T and you take RREF, you're going to end up with this guy, which tells me that all 3 coefficients end up being 1. Now you can put 1s in for the T and show that you're going to get like linear dependent here. But if T is not equal to 1, this guy works, and this is linearly independent. So the answer to my problem here is I am linearly independent for all T, which are elements of the reals, such that T is not equal to 1. All right, there you go. All right, so 6 gives you a set of 3 vectors. 1, 1, 1, 1, 1, 0, and 1, 0, 0. And it asks to show that this set of vectors is both linearly independent and spanning, right? And it spans R3. So linearly independent, we saw in problem 3, we just make columns out of them, right? Set those columns equal to 0, run our REF, run the Gauss-Jordan, and we get our happy little situation where all of the coefficients are 0. So this proves linearly independent. Okay, and if I build the matrix with the columns, by problem number 2, if I take the determinant of that matrix, which happens to be -1, which is not 0, this means that this thing has to span R3, and I have linearly independent and spanning by the same logic that you get in problem 3, and then again in problem 2. All right, so that's it. It's all 6 problems. I hope you're able to follow. If not, I'll see you in the drop-in session and try to answer some questions, and we'll go from there. Thanks.